Welcome back from break. Now we're going to practice that problem that I just mentioned to you guys, in which you are going to be given an IUPAC name that is incorrect, and you need to basically give the correct IUPAC name, okay? So for this, let's do the following example. Let's say that you have the following molecule: 5-methyl 4-hexene. Okay, so given this name, I'm going to write 6 carbons in a row, okay, because I have a hexene. My carbon-carbon double bond is between 4 and 5. And then the methyl group is on 5. So this is my condensed structure based on this name that it is incorrect. So let's put in the chat, let's forget that incorrect name. What is the correct IUPAC name for this? Is the molecule still a hexene? I agree with the name in the chat. That's the correct name for it. So this molecule is still a hexene, okay? It's just that it was numbered incorrectly in terms of how we number alkenes, okay? The correct numbering should have been 1, 2, 3, 4, 5, and 6. And like you guys put in the chat, the correct name for that is 2-methyl 2-hexene. Okay. So again, in the problem that we were doing before break, it's just that I drew the 1,2 cyclohexene instead of the 1,6. So we fixed that. But this question in the lab, it expresses, and the name that is given is only used for drawing purposes. It is not the actual name of the molecule. You need to rename it. And it will tell, the problem will tell, hey, this name is incorrect. Use it for drawing the molecule, but then rename it, okay? Any questions about a problem like this? I'm not gonna have this in the exam. Yeah, I don't understand your question. Would there be any problems that has you can
Like,
have, go ahead.
oh, sorry, no, I was saying like if the double bond was like in the middle, so it'd be equal distance, so it wouldn't matter where you, I guess, started counting, or would that be like a completely different name? If I don't know if I'm making myself
No.
clear.
So let's say that the incorrect name would have been 5-methyl 3-hexene, right? For example, then that means that if this is the incorrect name and we draw it out, then it will be 1, 2, 3, 4, 5, 6. So this is where the double bond is. This is where the CH3 is. Still, for this molecule, it will be incorrect if it's 5-methyl. Because according to the rules, just like you were pointing out, since this is an equidistant alkene, the methyl is on 2, not on 5. Does that answer your question? So understand that this problem is specifically for lab 9. I don't ask you guys questions like this in the exam. I just wanted to make sure. And I know that in the worksheet there, but I think I labeled it in the worksheet. It says like, this is the incorrect name, like just to give you guys one more practice of this. I don't remember which number on the worksheet specifically it was, but let me see if I can look it up. I think there's one in the alkenes, possibly, and one on the cyclic alkanes in the worksheet. But again, it's to help you guys practice for the lab. Excellent. So there's one more concept that we need to explore when it comes to alkenes, and that is the concept of cis and trans isomers. So one of the things is that whenever we have an alkene, we know that that carbon-carbon double bond actually cannot rotate. Having that trigonal planar electron group geometry in that carbon-carbon bond does not allow the bonds to do a full rotation, okay? So those atoms are fixed into positions, okay? So when it comes to cis and trans isomers, and these are just terms that maybe you guys have heard before, like you have heard maybe of trans fats, just because they're in food, okay? So we typically don't talk about cis fats because cis fats are the ones that are specifically in nature. But the trans fat, for example, maybe that term trans, you have heard it before. But what does it mean in terms of chemistry? Cis and trans are basically going to be There's a question, is trans fats due to the kink in the carbon chain? Actually, trans fat and cis fats have kinks in the carbon chains. It's just that, as we see here, cis are going to be looking towards the same side, okay, which it could be both up or both pointing down. Like if you see here, cis 1,2 dichloroethene, the chlorines are pointing up. That's what makes it cis. And then if trans is opposite, okay, which means that one is going to be pointing up and the other one is going to be pointing down in any of the two carbons across the double bond. That's what it is. But that's correct. Like in general, having a carbon-carbon double bond makes a kink in the molecule, but it doesn't matter if it's trans or cis. The kink will be there because of the carbon-carbon double bond in the fat. We will be talking about fats specifically in chapter 15, once we start our topics of biochemistry. So understand that whenever we're dealing with an alkene, alkenes have this ability to be determined if they're cis or trans. And when it comes to naming, understand that in the exam, I will incorporate cis or trans in the naming. So when you have an alkene, you can draw it, you can do everything you want, but in your drop-down menu, you're going to have to determine if that is cis or trans. So at least in practice, the only cis or trans that I give you guys are going to be in straight chain alkanes. Cis and trans do also exist in cyclic alkenes. They exist in cyclic alkanes too, but in this class, we're only dealing with straight chain alkenes to determine cis versus trans, okay? So let's actually show how to determine cis and trans in a molecule, okay, that we have that it is a straight chain alkene. Now, by now, we have practiced how to name alkenes, okay? And this is just a review of what we did earlier today. So if we look at this molecule, what is the name of the parent chain? Remember, this is the longest carbon chain that contains a carbon-carbon double bond. Pentene, excellent. I'll put a 1 in the chat if you want me to write in the carbons and hydrogens for anybody that needs that. Understand that I will stop doing that as we progress in the functional groups, just because it gets too busy depending on the functional group, but for now we can still do it. So there's a carbon right here. This carbon has a hydrogen. There's a carbon right here, and it has a fluorine, and that's connected to a CH2. It's connected to a CH3. Texas carbon. This is connected to a CH2. This is connected to a CH3. So taking this into account, we know that the last word in my name is going to be pentene, okay? Numbering is going to go in which direction, you guys? How do I number my alkene? Great, left to right. So it's going to be 1 pentene, and what's going to be the location and the name of those substituents? Great job. This is 1, 2 difluoro. Okay. Now there's one more thing that we need to include. Is it cis or is it trans? Remember, if we have something that is cis, the atoms across the double bond are going to be both pointing up or both pointing down, but I will tell you in a moment what that means, because we need to learn how to prioritize my groups across that carbon-carbon double bond. So let me just label, or let me just highlight the carbons across the double bond, okay? And let me just make a note here on the top for determining cis versus trans. What we need to do is, number one, select carbon-carbon double bond. Number two, list the atoms attached to the carbon at the carbon-carbon double bond. And determine high priority versus low priority. How do we do that? High priority means high atomic number. Low priority means low atomic number. Okay, let's start with that. So if I look here, I look at this carbon, I'm comparing fluorine to hydrogen. Who has the higher atomic number? Fluorine or hydrogen? Excellent, fluorine. So that means that fluorine is going to get the label of high priority group. Hydrogen is going to go and get the label of low priority group. Let's look at the other atom. We are comparing fluorine to carbon, because carbon is what is attached to the other carbon, right? So who has the higher atomic number? Carbon or fluorine? Great, fluorine again. So that means that fluorine gets a high priority label. This whole group where the carbon is at gets a low priority label. So when I look at my molecule, and I'm just going to redraw it, I have a carbon-carbon double bond that has a high priority group here, a low priority group here. I will color code it so you guys see what I'm talking about. A low priority group here, a high priority group here. Let me color code it. So this is this high priority group. This low is this hydrogen being a low priority group. This CH2 is this low priority group. This fluorine is this high priority group, okay? So does rule number 2 make sense? Put a 2 in the chat. If rule number 2 makes sense, we're gonna practice it with the 4 problems that we have here. Put a 2 in the chat if rule number 2 makes sense, how I determine high and low. I said put a 2 in the chat, not a 1, but thank you. It's okay, no problem. Only a few people get it, but that's okay. We're gonna practice, okay? Then on rule number 3, okay? Your trans molecules is going to be when the highs and lows are on opposite sides, meaning that you have high, low, low, high, or high, low, high, low, okay? Because your highs and lows are on opposite sides, okay? They're across from each other. They're not on the same, oh, wait, this labeling makes no sense. Give me a moment. The second one doesn't make any sense. Sorry, I'm making mistakes today, but if you have high here and low here, and you have low here and high here. So those two means that you have a trans arrangement, those two cases. In the case of cis, your lows and highs are going to be on the same side. So if this is your double bond, you can have high, and in the bottom, low and low, or you can have both lows pointing up and both highs pointing down. Okay, so the bottom so these are the two ways that we can get cis. This is how we can get trans. Okay, let's look at the next example. I select my carbon-carbon double bond. It's right here. Let me include the carbon atoms. There's a carbon right here, carbon right here. There's a hydrogen right here. There's a CH2 here, CH2 here, CH3 here. There's a CH3 here. Okay. So when I look at the carbon, let me zoom in. When I look at the carbon in the left, okay, what is attached to this carbon in the carbon-carbon double bond is a carbon versus a bromine. So who has a higher atomic number, carbon or bromine? Great, bromine. So that means that this is high priority. This is low priority. When we look at the carbon atom on the other side, we're comparing carbon to hydrogen. Who has a higher atomic number, carbon or hydrogen? Excellent. So this is a high priority group. This is a low priority group. Okay. So at first, we can determine, oh, okay, so this molecule, okay, we can see that if I rewrite this, my carbon-carbon double bond oh, I didn't write the trans here. Sorry about that. I have a low priority group. Here I have a high priority group. On the other side, low priority group, high priority group. See how the lows and the highs are in the same direction. Yes, you add cis or trans in the beginning. So what would be the arrangement for that one? Cis or trans? Excellent, this is cis. Okay. I know that is kind of crowded because I did the labelings for cis and trans. But what is the name of this molecule? The only thing wrong in that name will be the exactly. Not hexane, hexene. So this is 2-bromo, 2-hexene. Okay. Longest carbon chain is 6 carbons. 1, 2, 3, 4, 5, 6. Only one substituent. Let's just try this in a more organized way. You have the following molecule. Let's name it. Let's name the following molecule. What is the name of the parent chain? Great, octene. Eight carbons in a row. Let me highlight them. That's my parent chain. Where is my carbon-carbon double bond? What is the location that I need for it? Great. What about the substituents? I'm going to number it, but put in the chat the name for the substituents. This is 1, 2, 3. Great job. 3-bromo followed by 2-chloro, because we need to put them in alphabetical order. 3-bromo, 2-chloro, 2-octene. Now let's determine cis versus trans, okay? I have my double bond, I divide it in the middle. For those students that need the carbons, I'm going to add them. There's a carbon right here with 3 hydrogens. There's a carbon right here. There's a carbon right here. Carbon right here with 2 hydrogens. This is CH2, 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 and this is a CH3. Let's deal with the carbon on the left side. I'm comparing chlorine to carbon because are the atoms attached to the carbon in the carbon-carbon double bond. Who gets the high priority label? Cl or C? Great. This is high priority, this is low priority. Let's do the next one. We're comparing carbon to bromine. Who gets the high priority label? Great job. This gets a high priority label, this gets a low priority label. If I redraw this, that means that my carbon-carbon double bond looks like this. High, low, low, high. Is it cis or trans? Great. You guys are getting the hang of it. trans. Okay, let's do the last example. Let's name this alkene. And again, when you guys are naming this, you will see it in the chapter quiz. It's a drop-down menu. This is my longest parent chain. There's 6, great job. This is hexene. Okay. Which direction am I going to number this alkene? Great. 1, 2, 3, 4, 5, 6. Okay. So the number before the hexene, what would it be? Remember, this is an equidistant. Let me show it for the people that put left to right. 1, 2, 3, 4, 5, 6. This is an equidistant alkene. So that means that I need to then, because it's an equidistant alkene, give my substituents the lowest number. So that's why the red is the correct, not the blue. Let me erase the blue. In terms of the substituents, let's list the substituents in alphabetical order. Let me see it in the chat. What will be the number? And how do we list these substituents correctly? Great. 1 fluoro, 3,4 dimethyl, 3 hexene. Let's now do the cis and trans. Okay. I take my alkene, I divide it in the middle. Let me include the carbons and hydrogens. This is a CH3. This is a CH2. This is a CH3. This is a carbon. This is a carbon. This is CH3, CH2, CH2, and F. Okay. So let me deal with the carbon in the carbon-carbon double bond that is on the left first. The carbon in the carbon, so the atoms attached to the carbon in the left side of the carbon-carbon double bond are carbon and carbon. Okay, so that means that we need to look, since we are stopping at the same atom, we need to look at what those carbons are attached to. Okay, so if I'm making my list, the carbon atom that I label number 5, that carbon is attached to a hydrogen, and a carbon. For those students that don't understand the list, this carbon is this carbon, these 2 hydrogens are these 2 hydrogens, this carbon is this carbon. Okay. The reason why I'm doing this is because when I compare it to the bond that is pointing down, Here I have a carbon atom bonded to a hydrogen, and a hydrogen. Okay. Put a 1 in the chat if the list of atoms that are attached to carbon number 4 makes sense. Now we go through the list. We say carbon and carbon, same atom. Hydrogen and hydrogen, same atom. Hydrogen, hydrogen, same atom. Oh, I found a point of difference. A carbon atom versus a hydrogen atom. Who has the higher atomic number? So that means that that whole group that is pointing up, basically that whole bond of carbon 5 and 6, that is my high priority group. And the CH3 is a low priority group. Okay. So what would you guess when we look at the situation of carbon number 3? What would be the label of the CH3? Excellent. This is a low priority group. And then the CH2 with everything else that is attached to, that is a high priority group. Great job, exactly. Here we have the highs and the lows on opposite sides. So if I redraw this, my carbon-carbon double bond looks in the following way. Low, high, high, low. So that's why this alkene is trans. Okay. Put a 1 in the chat if you want to do at least one more practice problem before we move on to the alkynes. This is from the in-class worksheet. Did I give you guys cis and trans? No. No. Actually, let me use a different resource. Give me one moment. We have the following problem. Here we have an alkene. We need to name it, and we need to determine if it's cis or trans. Oh, when I made the list, the C in CHHC is the carbon that is holding the two hydrogens. So let me redo it. Too many colors. Let me see. Hopefully this will help. This carbon is this carbon. These two hydrogens are these two hydrogens. This carbon is this carbon because all of that is attached to the bond that is pointing up. Okay? This is kind of like when I use the analogy of when you go hiking. So when you go hiking, right, like it says you can take this trail versus this trail. So if you're standing right here, let me just do a stick structure. So if you're standing right here on carbon 4, okay, then this will be the trail to your right. This will be the trail to your left. The trail to the right is a carbon, 2 hydrogens, and then after that you see a carbon with 3 hydrogens, right? Like you could technically say, oh, and down here there's a hydrogen, hydrogen, and hydrogen. Does it make more sense? Like where the whole list comes from is basically all of the stopping points on that trail in, if you, use the analogy of hiking. While the bottom trail, if you look at what is there, you will see, oh, there's a carbon and there's a hydrogen, hydrogen, and hydrogen, because that's all you see down here. So that's where the list comes from. Is this the one that you need for the screenshot? Oh, okay. Awesome. So let's do this problem to at least practice one more time. Understand that this concept of cis and trans in the textbook is oversimplified. They just tell you, okay, both bromines pointing up, or both bromines pointing down, that's cis. Or if they are, opposite from each other, that's trans. But I'm showing you a little bit of a more realistic view of organic molecules. So we have the following molecule. Let's name it first. So take a moment and name it. I agree with the cis and trans. Okay, heptene, awesome. That's the parent chain. 1, 2, 3, 4, 5, 6, 7. I agree with the heptene. That's a great job. We need to number this. Which direction? Great, left to right, because we need to give that carbon-carbon double bond the lowest number. This is 1, 2, 3, 4, 5, 6, 7. Okay. We have 3 substituents. We have to put them in alphabetical order. My alkene, oh, change the ink. We have a 3-heptene, okay? Who comes first? Oh, I like what I see in the chat. Yes, 6, bromo. Then 4, chloro. Then 3, methyl. 3-heptene. Okay, to determine cis versus trans, divide the alkene in half. Let's deal with the left. By now, we've done at least an example. When you're comparing a CH3 to a CH2, CH3, what's the label that we put on the CH3, high or low? Great, this is low priority. This hole where we have CH2 and CH3, this is my high priority group. Then on the other side, here there's a CH2, there's a CH, there's a CH3. On the right side of my carbon-carbon double bond, I'm comparing carbon to chlorine. So who gets the high priority label? Chlorine or carbon? Excellent. Chlorine gets the high priority group. The carbon and the reds gets the low priority group. Okay? So that means that my highs and lows are pointing in the same direction. The high lows are in the top, the highs are in the bottom. So is this cis or trans? Great job. Questions about alkenes and how do we determine if they're cis versus trans? Since there are no questions, let's now move on to talk about alkynes, which is when we have carbon-carbon triple bonds, okay? So the rules for alkynes are very similar to the ones that we discussed in alkenes. We're gonna find the longest carbon chain that contains the carbon-carbon triple bond. Now, if we have an alkyne, our ending is going to be -ine, okay? So that parent chain, if you put the alkane name, you remove the A-N-E and you put Y-N-E, okay? So instead of -ane, it's gonna end in -ine. So rule number 2, we're gonna number the carbon atoms starting from the end that is nearest the triple bond, okay? Similarly, if we have a triple bond that is equidistant, then that means that we are going to start from the end that is the closest to the first substituent, okay? We need to indicate the position of the triple bond by giving the number of the first carbon in the alkyne, and then, as you guys know, we need to follow the rules that we know so far for substituents, okay? They're gonna be as a prefix of my parent chain. So we have the following alkyne structure, okay? So when it comes to alkynes, let's put in the chat, how many carbons in the longest carbon chain in this structure? How many carbons? Great, 7. Let's highlight those 7. Okay, so what is the name of my parent chain? Excellent job, heptyne. Okay, I'm going to number this from left to right. 1, 2, 3, 4, 5, 6, 7, because I need to start from the end that is nearest the carbon-carbon triple bond. So my heptyne is on carbon 3. Okay. Here I only have one substituent. So how do I illustrate it? What is the position and the name of it? Name and position of my substituent. Great. On 6, I have a methyl. Okay, so 6-methyl 3-heptyne is the correct name for this molecule. Okay, so let's practice. For alkynes, we do not have, well, there are out there alkynes that are cyclic. In this class, we don't name them. We only deal with straight chains alkynes. So let's go through the first one. What would be the name of the parent chain, including the location of the carbon-carbon triple bond? Great, 1-butyne. And what about the substituent? What will be the name? Great. 3-methyl. 1-butyne. Understand that the cis and trans business that we just discussed only exists in alkenes, not alkynes. Next alkyne, what is the name of the parent chain, including the location of the carbon-carbon double bond? Great. Two hexyne. Let me highlight the parent chain. Let me number it. What is the name for the substituents? With location and everything. How do we name the substituents in this alkyne? Awesome. Trimethyl. Four, 4, 5. So I'm going to write in the carbon so you guys get used to how to look at skeletal structures for alkynes. But you can go ahead and name this molecule. I agree with the parent chain. The parent chain in the chat is correct. Awesome, great job, you guys. What about the substituents? Mhm. Awesome, 3,4 dimethyl 1-hexyne. Let's try one more, right? I'm gonna write in the carbons. Understand that an alkyne is a linear molecule. That's why you see the bond that looks so long. Yeah, the name in the chat doesn't make any sense. It is 1-heptine. I agree with the 1-heptine. It's not dimethyl. If this is my longest carbon chain, then what are the names of my substituents? Great job. Make sure when you guys are doing these at home, it's specifically for the exam, you come up with your name. And if you see in the drop-down menu, your stuff is not in it, then there's something that you're not doing correctly. Although in the drop-down menu, you may see things that are not correct just because it's a little bit of everything. So for this one, we have a 3-ethyl 5-methyl 1-heptine. Question, you guys, naming alkynes. Let me illustrate something for you guys before I continue. Let me open Canvas on my side. So this is how you guys Canvas will look like in the nomenclature practice, if you go here for organic chemistry nomenclature and you guys go to this website, you can actually create your own quiz. And let's say that you want to practice naming alkanes, okay? This is actually from the University of Ottawa, okay? And then after that, no functional groups, alkanes only. You can actually create your own quizzes, and you see that it says it has available 51. So you can say, let me start the quiz. And you can see that it gives you this molecule. And when it comes to it, then you have to be like, oh, okay, this is 1, 2, 3, 4, 5, 6, 7, 8. This is octane. Submit your answer. Maybe it's because they want to capitalize. This N is because it's a straight chain. If you check on your answer, but it says octane, I didn't give you guys the N thingy here. If you see octane, you're good. But here you can design a quiz on anything. If you see E and Z configurations for alkenes, let me click on that. Only one functional group. E is trans, Z is cis. So this quiz, you guys don't have those. But this, you guys, this one you cannot determine cis and trans. That's a diene. This ones you guys can do. So at least there's some things that you guys can practice. You can create quizzes here. So it is a good resource for practicing organic nomenclature, okay? If you see multiple double bonds, we didn't talk about it in class. I'm not expecting you guys to know it. So like that one, don't. This one doesn't have cis or trans. This is two double bonds. This guys, you guys can do it. Not that. This you can do it for sure. This we didn't talk about it. So this is, at least it gives you some practice, okay? Just in case, if you want more practice from the in-class worksheet. Let me go back. Wait, I didn't update that. Let me change something. For some reason, it didn't save it. Let me select one of these so we can practice. Okay, so when it comes to drawing, do you guys feel good about this, or should we practice at least more? Put a 1 in the chat if you want to at least, do these, because I'm just trying to see, because from name to structure. Okay, people want to practice. At least Divya wants to practice. Anybody else? I have 20 students. I only see a 1. Whoever wants to practice, put a 1 in the chat. Okay. Awesome. Yeah, I'm doing the answer key today for worksheet 11. So you should see it posted by tomorrow morning if I don't do it tonight. No problem. Great. So let's practice these at least. First one, 4-methyl 1-pentyne. How many carbons do we have in the longest carbon chain for a pentyne? Great. 1, 2, 3, 4, 5. My carbon-carbon double bond is in between which 2 carbons? Great. Then my methyl group is on carbon 4. Now I add the hydrogens. There's 1 right here, 2 right here, 1 right here, 3 right here. Now, just to warn you, and the reason why you guys saw the structures in the skeletal form, this area of the molecule is linear, okay? So that's why you guys saw that the structures will look like that in that area, okay? And then there'll be a bond sticking out of there. That is representing this atom right here, okay? After that, we have tetrahedral centers. So then we go down and up. Let me number the carbons so you guys can follow. This is 1, 2, 3, 4, 5. This is 1, 2, 3, 4, 5. Put a 2 in the chat if the drawings make sense, because if not, I'll redo it. Excellent. And as you can see, our methyl is on 4. So then we do a line. Again, if my vertex is pointing down, then my methyl is pointing down. Let me redraw that 4. Okay. I'm just, again, showing you guys how to correctly draw this, just in case for any students that have to take other organic chemistry classes. Let's move on to the next one. Hexyne, how many carbons? Great. 1, 2, 3, 4, 5, 6. Where is my triple bond? Between which two carbons? Great, 2 and 3. Let me number them. 1, 2, 3, 4, 5, 6. Okay, I have 3 substituents. Okay, I have 2 methyl groups on 4, 1 methyl additionally on 5. Now I add in my hydrogens. CH3, 2 doesn't get a hydrogen, 3 doesn't get a hydrogen, 4 doesn't get a hydrogen, 5 gets 1, 6 gets 3. Okay, if we look closely, look, carbon number 1 needed 3 hydrogens because it only is bonded to the one of the carbons in the triple bonds. The 2 carbons in the triple bonds don't need hydrogens because it already has 4 lines, 8 electrons around them. Carbon number 4, it has 4 lines, no hydrogens. 5 and 6, on number 5, we needed 1 hydrogen. On 6, we needed 3 hydrogens. Let's move on to the skeletal. So remember, and I will label it just like I did the one above. My carbon-carbon triple bond is linear. So this is my triple bond. To the triple bond, I have a CH3. To the other side of the second carbon in my triple bond, I have a carbon atom with 2 substituents. So I draw a line to it. Now things start getting tetrahedral, so I can bend the bonds down, up. This is that atom. This is this atom. The only thing missing is my CH3s, okay? On the blue atom, we have 2 CH3s. Again, the one that I labeled in blue, because the vertex is pointing up, 1 CH3, another CH3. The one that is yellow, it has 1 CH3 because the vertex is pointing down. That is the CH3. Okay? Put a 1 in the chat. I know that I colored this, so it should make sense, but I want to make sure that it makes sense. The skeletal. Yeah. Anything attached. It's just that, oh, a carbon-carbon triple bond is linear because you only have 2 electron groups, right? The carbons are held together by a triple bond. A triple bond is 1 electron group, and whatever else is attached to it is a single bond to complete the octet in carbon. So that's why you have 2 electron groups. That is linear. So again, look at this atom. 1 electron group, the triple bond. 1 electron group. An atom with 2 electron groups is linear. That's why it's linear. So alkynes are linear. The main thing, remember, in this class, you guys are not going to be drawing anything necessarily. But what I want to illustrate is that when you guys get these, which again, when I generate these, I use my, I have a special program for drawing molecules. And if you guys are dealing and naming something that has been given to you, skeletal structure, I just don't want you to be confused into the number of atoms that are there. And if I choose to give it to you on condensed form, it's a little bit more straightforward, but in case I give it to you skeletal, you need to know both ways. Let's just do one more practice before I let you guys go. Let's do the last one. The 4-bromo, 4-isopropyl, 2-heptine. How many carbons in my longest carbon chain? Excellent. 7. 1, 2, 3, 4, 5, 6, 7. Between which two carbon atoms is my triple bond? Great. 2 and 3. Then I have 2 substituents on carbon 4. I have a bromine and I have an isopropyl. Let me add the hydrogens. This is a CH3. This is a CH2, CH2, CH3. Let's go to the skeletal. 1, 2, 3 for my triple bond. This is the CH3 that is sticking out of it. This is carbon number 4, 5, 6, 7. Out of carbon number 4, I have a bromine. And remember that the skeletal form of isopropyl, what does it look like? What letter does it look like? Great, a Y. That's how we draw isopropyl. Just for those students that benefit from the color coding. This is this. This is this. This is this atom. Any questions going from name to structure for the alkynes? Excellent. So this is all for today.